What's the F ratio on one of those things? Faster than you'll ever be, pal. Apo, F5.9. Smoke 'em. Woo! Welcome back to Deep Sky Labs. Okay, quick confession, that opener was originally intended to be super silly because honestly, I didn't think F ratio was going to change my typical nights once you factor in sky glow, light pollution, clouds coming and going, how much time you can actually get out there, collimation, the usual chaos. I went into this thinking that F2 was going to be kind of a cool video to make, show off a cool piece of hardware that I have, but it wasn't going to be, you know, a real world game changer. I expected a tiny edge at best. I knew it was going to make some difference, but you know, once you factor in everything, I assumed my response was going to be just stick with like a nice, clean, tight refractor. That was my bias going into this, and I was fully prepared to dunk on the hype. Turns out, past me was adorably and glamorously wrong. Let me show you why. Let's start with a quick refresher on what even is F ratio. It's really simple. It's a made-up construct. It's just the focal length of a telescope. So how long does light go from the first optical element to the output of the telescope, divided by the aperture. How wide is that first optical element of the telescope? A lower F number means that the cone coming in, ends up being sort of a lot wider. Which in theory means that each pixel probably gets more sort of photons per second. Anyways, the textbook rules give us a really clean baseline. To reach the same brightness, exposure times scales by F squared. So in what we did in this experiment, F2 versus F5.6, in theory, the F2 telescope would be as bright in 7.8 times less time. And in typical sky limited imaging, the books say that the SNR per hour scales roughly with like 1/f. So F2 should yield only about 2.8 times more signal to noise ratio, SNR, per hour than F5.6. Those are ideals. The sky, your filter pass bands, and your workflow sort of shave those down, but that's the target that we'll measure against in this video. All right, I want to talk about Hyperstar for a minute here. This is the Hyperstar for my C11 Edge, but it's essentially just a slightly bigger version of the Hyperstar we used in these experiments. It's actually still out there on the scope right now. What the Hyperstar does is it replaces the secondary mirror on an SCT. So on an SCT telescope, there's that first big sheet of glass, which is the corrector that light goes through. It bounces off the big mirror in the back that you can see to a smaller mirror, again on that front side on the outside, and then bounces back down to the, either your eyepiece or your camera or what have you. What the Hyperstar does is it replaces that the secondary mirror, so the mirror that's on that big piece of glass in the front, with a bunch of lenses. And what these lenses do is they sort of fix the light. So the light at that stage would have a ton of coma, like a bunch of optical aberrations that are usually fixed by that second mirror that's there. So when light hits that mirror and bounces to the camera, it's sort of being fixed along the way. Now, this idea traces back to Celestron's original Fast Star, which was something they produced in I want to say it was like the 80s or the 90s. Back then, those CCD cameras were really tiny. Like they were really small cameras, so the correction wasn't huge. The optics weren't that advanced. Like definitely not anything as crazy or as heavy as something like this. And they sort of gave it up, but a company called Star Arizona in Tucson, Arizona took up the mantle, and they created this Hyperstar line. You can get these for everything from the 6-inch to the 14-inch telescopes. The trade-offs, though, are real and serious. At f2, everything becomes a lot more critical. So your back focus spacing, your tilt, your collimation, and as I discovered, your flats become a lot more important to the final quality of your images. Even things like cable routing can affect how the stars look, because those cables, if you put a camera here and this whole thing's sticking out the front of your telescope, those cables have to pass in front of the light path. So, you know, you've got to be really careful with it. But if you treat it like the race engine that it is, you check your tolerances, you keep it tuned, the payoff can be huge. What you get is an unusual combination in telescopes. You get, you know, the aperture of something that has a really big mirror and a really short focal length. There's not a lot of telescopes that are at f2 that don't have a mirror. Basically, there's not much that's not Hyperstar that's f2 in these apertures. The combination is the sort of thing that people dream about when your clear nights are rare and short, in theory. You do trade some of that simplicity, right? Because these are complex for speed. But, you know, to my understanding, on the right night, you know, under the right conditions, that speed could buy you back a bunch of time. I assume that on average, that wasn't what happened. The key to unlocking that speed, you know, isn't some secret setting. Turns out it's calibration. So the test was meant to be really simple. I put the Hyperstar on the C8, put it out under the night sky, and was gonna just basically drag race it against William Optics Z61 II, which is a great entry level, you know, refractor. It's 61 millimeters and about the same focal length. So I was like, all right, the framing will be the same, and it really does come down to, like, on any given night, is it worth the hassle of bringing out the SET, or should you just leave your refractor out all night? We use the SVBONY 605cc, which is a 533 class sort of sensor. We use the SV220 dual narrowband filter because the moon was out a little bit. We weren't pointing terribly near it, but it was still out. And we did half-second guiding with a dither every 3 frames. We shot the Veil Nebula because it's pretty perfect what we captured for around 400 millimeters. I'm very familiar with that target, so like things would pop out immediately to me. It's got that nice sort of face profile, and there's a good mix of light and dark depending on, you know, how much time you spend on it. You can really start pulling out a bunch of additional details. So let's put up on the screen here the auto-stretched images with no flats. And you can see here, it looked like my bias was right. The Z61 looked better. Now, they had the same total integration time. The Hyperstar was shot with 60-second subs, and the Z61 was shot with 300-second subs. I only made that difference because I didn't want the Hyperstar, like the stars, to blow out on the Hyperstar, so I wanted to shorten that. But they ended up with the same total amount of integration. So I did a quick actual like check with Cyril has a tool where you can check the statistics of any sort of given area. I've done this in the past when we were comparing like cooled astrocams to DSLRs and things like that. So when I did the SNR check on just those uncalibrated stacks, so I you know, grabbed all the images, I registered them, I stacked them, and then I selected a dark spot and a light spot to calculate sort of signal to noise per hour. The Hyperstar barely pulled ahead, and sometimes it felt neck and neck. I was this close to just saying, ship it. We're gonna, you know, shoot the video. We're gonna say, see, F ratio doesn't really matter in the real world. But those images that I was looking at were telling me something, that the reason that the Hyperstar wasn't performing well, you could see, was uneven illumination. It wasn't about speed. So now it's time to out myself, my dirty little secret, as someone who has done astrophotography for about 1.5 years now. I've never taken flats. I had a old ASI 294 MC color camera, and I took dark flats for that because you had to get rid of the amp glow. But even then, I sort of just did it whenever I could. To me, the solution to not taking flats was just crop out any of the dust or any of the vignetting. It's fine. It doesn't really matter. I really needed to do flats. So I did the, what is to my mind boring but essential thing. I shot the flats today, actually. I just did sky flats. I pointed it up at zenith at around 11 a.m. There's no clouds in the sky. It's a perfectly blue sky. I used the flats wizard in Nina, and sort of until I got the histogram to be in the middle or a little bit less than the middle. And I stacked those in Cyril, and I sort of, now I have my like master flat. I did the same thing for the Z61 because I do still want it to be apples to apples, but this isn't sort of a how-to video on how to do flats. I'm actually going to do that as my next video because I just did them quick and dirty. But even my quick sky flats made such a huge difference that I think I'm a convert to you need to take flats all the time. The background noise on the Hyperstar dropped dramatically, and the faint stuff that's in like those edges of the really bright nebulosity stopped having to fight gradients to really come out. So I'm just going to show you guys the images here left and right. Yeah, see, look at how much of a difference that made. The Z61 now doesn't look, you know, oh, it's about the same quality, maybe it's about as fine. Like, no, it's very clearly not as bright. So I then took those images and I measured SNR using linear masters. So you'll see it looks bright in these, but that's just because there's a screen auto stretch applied. The image was still linear, it hadn't been stretched at all. Using the same ROIs, you can see the screenshots here where I show that. I use this small nebula patch for the signal mean, and then a nearby blank sky patch for the background median and the background sigma. And then I sort of normalized all that to SNR per hour because there was a slight, I mean, there was a difference of like 5 minutes between the two because I had to throw away a couple frames on the Z61. So Hyperstar SNR per channel, RGB, 11.54, 32.88, and 21.67. Well, let's say the average is about 22.03. Now, these numbers are really only useful in this context, so don't write these down and assume you have to go get something similar. For the Z61, the SNR per hour was 4.8, 13.6, and 9.6, with an average of about 9.17. That's roughly 2.4 times more signal ratio per hour for the Hyperstar in my real night sky over the last 2 nights. So in plain, SNR with something like this is amazing. And because signal to noise ratio grows as the square root of how much time you're under the stars, with a 2.4x SNR per hour advantage, the Hyperstar needs 83% less time under the stars for the exact same SNR. To get the Z60, I did some like back of the napkin math. To get the Z61 to match this signal to noise ratio, I'd have to leave it out for 12 hours. As a reminder, this thing was out for like, I think it was like an hour and 50 minutes. To get the same, I would need 12 hours to match it. That's crazy. So once you get something like this, and once it's calibrated, it didn't just win, it kicked its butt. And it really opened up the potential to me to be able to shoot really interesting big targets very, very quickly. So why did flats change everything? I assumed that flats were there just to get rid of dust spots, to be honest. That's what I was like, yeah, you do flats because you didn't do the job of cleaning your, you know, equipment and you want to get rid of the dust motes, yada, yada, yada. At f2, the sort of light cone coming into the sensor is, you know, it's really wide. There's a bunch of really interesting optical phenomenon, but essentially the vignetting really gets inflated when you're shooting this fast, especially when you're shooting with a mirror this big. And what happens is that vignetting really affects the measured background noise. And so when you apply flats, you can see the difference in the images. It really like brings that almost like a haze down, and that lowers the noise ratio, or the noise part of that mathematical equation. So correcting the field really matters at f2. I did apply the flats to the Z61 as well. It didn't have as much of an effect, which is something I want to investigate in my flats video. Is like, does f ratio really matter? So I can measure from f2. I have equipment, or I'm sorry, I have telescopes from f2 all the way up to like, I don't know, I think I have an f12 somewhere that we can see what the effect that flats have. So yeah, this video and producing this was really my, I was the bottleneck moment. I thought the sky was eating the speed in those first images I saw. I was like, yep, I knew exactly what I was talking about, but there was something there that was really bugging me and I needed to dig in. It turns out that my calibration sloppiness was eating a big chunk of the speed. Once I was able to fix that, the math and the sky mostly agree now. Fast optics, didn't really change my night, because if I just kept imaging the way I was imaging, I would have ended up with basically the same results. It was calibrated fast optics that are really going to change the way that I do astrophotography moving forward. So here are the final calibrated stacks with similar stretches. The Hyperstar pulls out these really nice, delicate filaments in the HA and the O2 structure really quickly. And you can see the surrounding sort of nebulosity bloom even in these short sessions. The Z61 though does shine for effortless, clean stars, predictable corners, minimal drama. When I travel, I'm still going to travel with my Z61. I'm not bringing my C8 with me on vacation, at least not yet. And I do love it for that. There's a reason that we love these small refractors. On really tight weeknights or between clouds though, that Hyperstar, again, if you calibrate it, will get you usable, fast images. Now, if you're looking for something way more relaxing where you don't have to do a bunch of collimation, that Z61 is still like relaxing on a nice cruise. But this Hyperstar is like driving a race car. Like, yeah, it's going to take a little bit more, but if you do it right, it's so gratifying. Fast optics didn't change my night. Calibrated fast optics did. With flats, the Hyperstar landed at around 2.4 times the signal to noise ratio per hour of the refractor, which means, it's crazy, the math is crazy, the same image quality in 17% of the amount of time. That's the promise of f2, but there is that catch with f2. Flats are the price of admission. Skip them, and the vignetting and background noise will erase any of the speed you paid for on anything but the most pristine nights. So my verdict here is simple, and also a little complicated. Speed is still king, right? There's no replacement for aperture if you do your flats. The refractor will always stay my peace of mind rig, but this Hyperstar is like a time machine for me when I'm disciplined. So for each night, I think I'll pick the tool and the workflow that fits the night. But I'm definitely a lot less scared of the Hyperstar, and I'm becoming a lot more grateful for the concept of flats. And that is going to be one of the videos that I do in the future. So if this helped, hit subscribe. In the next episode, like I said, I'm going to be documenting my journey to flats, specifically for fast optics. I want to put this on the C11 and sort of see what that looks like. I think I want to compare it to a William Optics Z61. So almost the same experiment, but sort of moving up a class of aperture. I want to show everyone what I'm going to try, what broke, and any simple checks that sort of prove that your flats are working, so nobody else has to learn it the hard way. I'm going to be referencing Quiv's video. He did a really good video recently on a lot of the concepts behind flats. So I've been watching that one over and over again. And if you do want to fuel more real sky experiments, I have a buy me a coffee link down in the description. Clear skies and go fast responsibly.